I would like to get started. I got a lot of different things to do today. My goal is just to make sure we get finished 5-2. And so here is something that we've covered, but a little bit more formally. And it's what we call indefinite integrals. We're still on the usual problem. Here's a function, y equals f of x, from x equals a to x equals b. And we would like to know what we call the area under the curve. Now, the area under the curve in this picture, the entire curve is above the x-axis, but there's nothing to stop a curve going below the x-axis. So it is possible, and you will find them, and not today, but well, probably not today, but certainly you will find them in next week, that the area under a curve can be a negative number. It can also be 0, couldn't it? Can you imagine the top half being the same area as the bottom half? So I've just done that because it's easy to draw. And this is called the fundamental theorem of integration, part 2. So obviously there's a part 1 that you don't know about, but I'll tell you that next week. Part 2, the one we're about to do, is actually the important one. Part 1, you don't use it much. So it's not as important. So what does it say, this theorem? Well, if you've got a smooth continuous function, right, a nice curve, so you can't have vertical asymptotes in it. Can you imagine the area under a vertical asymptote could be a problem? Right, so you don't want curves that do weird stuff. You don't want, I don't know, curves that are broken apart either. So we just cover ourselves and say, okay, it's a nice smooth function. From x equals a to x equals b, then the integral from a to b of f of x dx, that means the area under the curve from x equals a to x equals b of this function is equal to the antiderivative at b, take away the value of the antiderivative at a, and capital F of x is the antiderivative. So you remember right at the end of yesterday, we were doing some practice at finding antiderivatives. Yeah, like the antiderivative of x squared was the third x cubed, right? That kind of thing. So how would you apply this fundamental theorem to find, say, these two, which are actually examples of questions from that homework? So if I want the area under the curve of x squared between 0 and 5, and I decide to use this technique, then there's the guy. The antiderivative of x squared is 1/3 x cubed. Can you remember how that rule worked? It's called the power rule. Add 1 to the power, so now you have 3. Divide by the new power, you've got 1/3. Are you comfortable with the antiderivative of x squared being 1/3 x cubed? All right. Now, the formula says the antiderivative at b, take away the value of the antiderivative at a, and the way it's typically done, and almost everybody I know at least, is you, for convenience, you just draw a big vertical line and you write x equals 0 to x equals 5. And that's your way of showing you're working. You're saying, look, I'm going to do this, fella, and I'm going to evaluate it at here, and then I'm going to take the answer away from here. So if you look on the next line, can you see that's basically the antiderivative's value at 5, take away the antiderivative's value at 0. And if you calculate that, you get the exact area under the curve. Now, considering the techniques that you've been doing before, would you agree that that is a really clean algebra? Thank goodness I don't need to do 20 strips anymore, right? I've seen enough of them and I just don't want to do them again. This one is another example, a little bit simpler actually, I would say. The area under the curve from 0 to 2 of the function 5x. Well, if you want to do that, you find the antiderivative of 5x. So add 1 to the power and divide by the new power. So that's the antiderivative. Evaluated at x equals 2 to 0. Plug in the 2, so the value of the antiderivative at 2 is 20 halves. That's nothing, so 20 halves take away none. The answer is a nice round number. It's 10. So you can actually find the area under any curve that you could possibly want. Let's do another one. I would like to know, I'll draw a little picture of it, just feel like it. I would like to know the area under the cosine function in radians, of course, from 0 to pi upon 2, right? For some reason, I'd like to know that. That would be the displacement of a moving object, perhaps. The integral from 0 to pi upon 2 of cosine x dx would represent that area. Okay. What is the antiderivative? So this is a question. What is the antiderivative of cosine x?
It'd be sine x, right?
Correct. It would be sine x, correct. Think of what function do I need to go here, right? The antiderivative. That if I differentiated this, you get that, right? Antiderivative.
Did he explode?
Maybe his Wi-Fi cut out.
He exploded.
So then it's not just me.
Yeah, no, he exploded. Oh, you're the host now.
Wow. Oh, this is actually pretty cool. I can mute everyone. No offense, guys, because you're a pretty loud crowd. Just saying.
You have to teach us how to take the antiderivative of cosine and whatever that was supposed to be.
No. But does this mean I have to let him in? Like, should I be looking for something? You're the IT guy, James, so you have to help me.
I don't know how Zoom works. And he's probably able to get back in.
No, because he
Eh.
has it so that the host has to let people in individually.
Who's
geez.
Christopher Thurman? Is he in our class? Because now he's in the meeting.
Well, we're awake now.
I'll do that, Eric. I'll do it from my phone, though. Should I just use the same link?
The same link would lead you here, right?
Yeah, that's what I'm thinking. But I mean, theoretically, he has a great idea.
Do you know how to look at the weight room?
No, can you share?
No, I don't know either. Does anybody know?
I'm gonna Google it.
Stefan just came in. I think he's in our class.
So there's a manage participants button somewhere. So that's where you would admit somebody from the waiting room.
Okay, I'm looking for it.
It looks like it's in the bottom to the left of share screen. I'm like looking at YouTube
Bottom to
videos.
Like this side? No, left. This side.
Its picture is
I guess I'm your comic relief for today.
okay. So the participants button turns into a manage participants.
What? Oh. Yeah, but that's just like what you regularly get if you hit the participants button.
Yeah, but now you should
Let
know
me-
what to manage from there as well.
Oh, okay. Okay, so just keep talking, James. I'm gonna see if I can do something.
Oh,
Just keep talking.
but
Oh, no. I can't fix it.
it's fine.
Sorry. That's always seemed like it would be a fun choice to make.
So in theory,
I
he'll
don't
show up
s-
there.
I don't see the waiting room at all. Like there's a little
Oh.
banner on the top of the screen. Whenever someone comes in. Here, you know what? Oh, jeez. Nope, that was the wrong button. That's not even what I selected. Crap.
He hasn't sent a message on Canvas yet, so
Hi guys, I am back.
He's back.
Oh, thank goodness.
Yes, I don't know. I guess it must have been a little bit of extra power, or who knows. I think we're entering that place where 2 leaves fall on an electric cable, and you're 6 weeks without power. Well, okay, that's an exaggeration, but I'm back. Well, now who took over, James? Were you the one that took over the class and
Yes.
filled in the gaps?
yeah, we're definitely talking about math.
Okay. Okay. God, you know how easy it is to distract me. A thing like that will throw me for about 10 minutes now. But anyway, I'll try and get back to. I was in full throttle there. I was having fun, and then I don't know where we get cut off. Did you see 1 and 2?
Yeah,
Yeah. Did I finish this, or did I kind of disappear somewhere in here?
you disappeared as soon as the last thing people heard was me saying sign X. And then if you had a response to that, they didn't hear it.
0 and pi upon 2. So that's what it would look like. And it's, oh, that's not good. Your internet connection is unstable. Okay, guys. So I'll just keep going till it does whatever it does. So we have the sine x from here to here, right? The antiderivative of cosine, as James was saying, was sine x, which it is. We evaluate it from x equals pi upon 2 to x equals 0, and that will get us the area we want. And the sine of that is 1, the sine of 0 is 0, and so this guy is 1. So that fella in there is 1. So what else is left? Well, section 5.2 homework kind of does a little bit of this and a little bit of that. So I guess the way to show you what the heck's going on is to just show you some of the questions in the homework and what you're expected to do. Okay, I hope you're looking at 5.2 indefinite integral. Okay, now, yeah, I know you don't want to do these, but you're going to do them a little few more times. Here is a table of values, and you are going to do 5 equal subintervals, just another way of saying 5 strips, right? So you're going to find the area of this curve from the beginning to the end, and you're going to do 5 strips. And it says lower estimate and upper estimate. What do you think you're going to do to get a lower estimate and an upper estimate? And there's 5 guys you can use. Left 5, right 5, mid 5, trapezium 5, Simpson 5, right? There's 5 things you could use. But which 2 are you going to use to get an upper and a lower estimate?
It looks like left would be lower, right would be upper.
Right. And you can tell that because the function's increasing. Agreed?
Yeah.
Right. And this guy, you're going to do a midpoint 4. This guy, you're going to do a midpoint 4. And this guy, you're going to do a midpoint 4. So the first 4 questions are actually back to doing the boring stuff, right? You know, just 4 strips. Well, at least it's only 4, right? That's something. Now, here is a guy from yesterday, right? It's a Riemann sum. Remember those guys that you make go infinite and it gives you the exact value, right? It's one of those fellas. All you're going to do here is fill in the information that should go here and here. So I'm going to start with the easy one. Since the interval is from 0 to 8, would it make sense that that number there should be 8? Now, in here should be the f of x. If you look at this expression here, can you see that that basically is the f of x? And you type in, let's see if we can get this done, fraction. On the top, I think you need to do e. Let me find out. Yes, e to the power of just x, not xi. X, oops, that's capital. Just x. And then on the bottom, 5 plus 6. So it's not that bad, right? It's a very quick thing to answer. And the same thing for that one, and the same thing for that one, and the same thing for that one. So that's that little bit done, right? We've done a version of that, and we've done a version of that.
Can you go back up to the first one real quick? Once they straighten it out.
Sure, there you go. So all you're doing here is taking a Riemann sum and recognizing what it would be if you were trying to find the area under a curve. So in question 5, you're wanting to find what e to the x over 5 plus x. Oh, have you noticed that they're using xi, you know, x1, x2, x3, xi, rather than the b minus a over n? They sometimes do that version as well, don't they? But when they do that version, it's kind of a little bit harder to see what's going on. But when it's written that way, basically, if you turn an xi into an x, you're done, right? That's the simple thing. So if I was doing this one, wouldn't it be x the square root of 5 plus x cubed? And wouldn't that be 2 to 8? Why do I know it's 2 to 8? Because of that, right? And eventually, we get to questions 9 and 10, which we kind of covered at the start. Right? We're using basically our definitions, our fundamental theorems. I'd use these ones, the ones I've just did. And now, somebody that's new. Here is a function, f of x, and we're being asked to evaluate some integrals. And we're going to do it using geometry. We know how to find the exact value for rectangles, triangles, and bits of circle. So if you went and asked me to get the area under this curve from 0 to 8, wouldn't it be this little shape here? Great. From 0 to 8. Now, if I was doing this shape, there's more than one way to do this. I would think of it as a little rectangle in the bottom and a triangle on top of it. That would be the easiest way to do that trapezium. Now, the rectangle in the bottom is actually 8 times 4. Would you agree that's 32? Right, it's not 2 boxes because there's a scale here, isn't there? It goes 0, 4, 8. So it's 8 units long and, 0, 4, 8 can up to 4 units high. So that would be 32. And if I wanted this triangle, wouldn't it be half the base times the height? And if you went from here to here, that's 8. And here to here is also 8. And a half times 64 is 32. So the final answer would have been something like 32 for the rectangle plus 32 more for the triangle. I don't know where that sign came from. And all you would be putting down is equal to 64. Now, do you notice that some of this curve is below the x-axis? Right, from what's that? That's going to be from 20 to 36. If you want to find any of these areas, let's do this one. Suppose you wanted to do from 20 to 28. That would be this piece of the curve here. Wouldn't it just be one big triangle? Right, its area would be 8 by 12. Now half of 8 by 12 is 48. But the answer would not be 48. Be almost 48, but with a change. What would the area under the curve from 20 to 28 be?
It would be negative.
Be negative. Right. Now, and I'm sure they'll do it. See when you get to some of these weird ones at the end? If you wanted to find the entire area, sorry, question. If you wanted to do from 0 to 36, wouldn't it be probably a good idea to find all the positive areas, break it into strips and rectangles and triangles, whatever it takes, and then do the same to this part. And then remember, this answer's positive and that one is negative. And that's essentially what you're going to do there. So if you know how you get areas of shapes like rectangles and triangles, you're good to go. And then they done this one to you. What's weird about question F?
It's
The
backwards.
zeros on top.
Yeah, it's backwards. Now, if I just found the area from 0 to 8, the usual way would be that guy. Remember the answer we got was 32. But the answer is from 0 to 8. This one is going backwards. What do you think the integral would be if you switch the order in which you start and finish? So it used to be 32 when you did it the normal way around, 0 to 8. What do you think it's going to be when you go from 8 to 0?
Negative.
Say again, James?
Negative.
Yes, that's all the difference. I can't think of any example in the world where I would want to find the area in this kind of reversed order. But mathematically, it does have a meaning, so I guess they threw it in for that reason. Now, in question 12, you are basically doing the same thing. Do you notice that this shape has got half a circle in it? Agreed? So it starts at what number is that? 1, 2, 3, 4. So, okay, that's 10 and that's 30. Suppose I wanted to get the integral from 10 to 30, right? The area under the curve from here to here. Wouldn't I just find the area of a circle and half it? And stick a negative on it when I was finished, because it's below the x-axis. What's the radius of that circle?
And
10. So wouldn't its area be, if it was a complete circle, wouldn't it be pi r squared? Pi times 10 squared, 100 pi. But since it's only half a circle, won't it be 50 pi? And since it's below the axis, it's negative 50 pi. And if you hit, well, I should be able to do it. This isn't the right one, but I just want to do it so I can do it. If I want to do negative 50, if I go looking under the Greek symbol, do you see I'll find my pi? And we don't want to know that it's, I don't know what 3.1412 is times 50. We don't want to know the decimal answer. We want to know perfect answer. So when things are exact values, it's okay to have square root of 7 as an answer. It's okay to have negative 50 pi as an answer. It's okay to have e cubed as an answer, or for that matter, the sign of 1. So don't get too caught up on the engineer's mindset as everything has to be a decimal or a number or a fraction. In mathematics, when we want exact values, we try actually to avoid those things, unless that's what they're equal to, right? So 50 pi or minus 50 pi is exactly what we want. Are we comfortable with this kind of, a little bit of this and a little bit of that section? Was there anything that we covered that you're not comfortable with? Can I call this section done then? Is there any questions on it? Okay, good. Because what that gives me is some time to look ahead and get a head start on next week's homework. Now it's still, so all you need to do is get up to 5-2 finished and you're getting your 0.5% extra credit plus your homework grade. But if you want to work ahead, feel free. It's available. If you don't, that's fine too. We are going to focus on the time that's left today with finding antiderivatives. Right? And I'm going to put down the kind of the obvious ones. The first one I'm going to put down is probably the most useful one of all the ones I'm going to put down. If you want to find the antiderivative of 5x squared or 4x to the 20 or anything you like, this is your guy. It's called the power rule. You add 1 to the power and you divide by the new power. And that's the one we are going to see a lot of. So let's show you antiderivatives. If I wanted to do 8x to the 5, and I want to find its antiderivative, that's all we're doing right now. According to the power rule, you add 1 to the power, and then you divide by the new power. And right now, we'll stick to the convention that you have to finish with a plus c. And that's called the arbitrary constant because, remember, I think we said it yesterday, if you differentiate this plus 4, won't you get that answer? But if you differentiate this plus 20, you get this answer. So one of the problems with an antiderivative is that it loses a piece of information. You do not know what value the constant term would be because it could be anything. So we cover ourselves to doing plus c. When we did the integral, remember we did the integral from 0 to 1 or whatever, why didn't I bother writing all those plus c's in? Technically they're there, but we just don't bother writing them. So if I did the integral from 0 to 1 of that function, I would only write this piece and then evaluate it to x equals 0 and x equals 1. Why do I not need to do plus c's when I do my working for areas under curves? Okay, let's show you. Right, here's one. Show you why you don't need it. Take that question I did a few minutes ago. The antiderivative is 1/3 x cubed. Let's suppose I did put the plus c in. Well, if you plug in 5, you get 1/3 5 cubed plus c. Take away 1/3 0 cubed plus c. That gets you 125 thirds plus c. Take away nothing plus c. Do you notice what happens to the plus c's? What happens to them?
They
It's not-
cancel.
They cancel out. And it's not this one particular question that they cancel out. Can you imagine that they're going to cancel out in every single one of these questions? No matter what you start with, when you do the antiderivative plus c thing, don't the c plus c's cancel out? So the reason why we typically don't do them when we do examples of area under curve is just because we're lazy. Right? You know, we don't need to do it, you know, when we do integrals, because it's not going to be there. But we're kind of pernickety as well in math. So when it's not involved in an integral, right, an area under curve, we should put them in, and it's expected. Well, how about this function? I'd like to find the antiderivative of 4 square root of x's. And you might think, well, I know how to do x cubes and x to 5s, but I'm not quite sure how I'd find this fella. Well, what you do is you convert them into an equivalent fractional pair. Now, I haven't done anything yet except rewrite the square root as a half power. Now I do the antiderivative and I use the power rule. And I think of the power rule more in terms of words than this formula. And what I say is add 1 to the power and then divide by the new power. If you take 4 and you divide it by 3/2, isn't it the same as multiplying by 2/3? Right? Dividing by 3/2 is the same thing as multiplying by 2/3. So what we get is 4 times 2/3. So the answer ends up being 8/3, which is that guy with a plus c. And then we do style points. This is the answer. Style points are really just my made up name for, we want the answer to be in a consistent form so that someone in Japan, in China, in France, when they do the exact same math, would be expected to write down the answer in the exact same way, right? We're very pernickety in math about how you write things. Off the top of my head, don't we never write 1x? Doesn't everybody just write x? We've all got this rule, things should be called x. Don't we like to factor things in math and put them in order when you do quadratics, right? Wouldn't most people say 2x plus 5 plus x squared would not really be a pretty way to write that question, right? We don't want people in other worlds or other countries having to figure out, is your answer my answer? Because I write it one way and you write it another. So just think of it, you got to do it. There is another style point rule, which I have just noticed that I broke. Would you agree that it makes sense that fractions should be in their simplest form? So I should have called that guy 4/3 x to the 6. So we can find antiderivatives of square roots, cube roots, and fifth roots. How about finding the antiderivative of that guy? Any suggestions on a different way to write it?
You could put x to the -3.
What, and that's exactly what I would do. What's good about that method, Amber? Why is that a more useful version?
So that you can follow the
Power rule.
yeah, the power
A bit
rule.
more in your
It's the
mouth,
same
but I know what you
form.
mean. Yeah. Isn't the whole goal here to get it into the power of x? X to the half, x squared, or x to the -3. If you can get it there, you're pretty much halfway done. Now, the antiderivative. Okay. When you add 1 to -3, you get -2, don't you? I almost did -4 there, but I stopped myself, right? You get -2. And if you then divide by the new power, which I'll do in my head, you get that with your plus c. And you always should finish with power rule. Style points. This guy is not in the form that we want. So let me give you a couple of the rules. The first probably major rule in the style point world, make your answer look like the original, right? So if your original had square roots, your answer should have square roots. If your original was a fraction, your answer should probably be a fraction, right? That's the first rule. The other, that's probably, of all the rules, that's probably the most important one. The next rules are obviously things like simplify your fractions and things like that. And then the last rule is factor the heck out of it, which hasn't happened yet. But occasionally you might be able to make it look prettier, you know, by taking your big long expression and factoring it and making it look a little bit prettier. So this guy, that one there, is your answer. So this rule called the power rule can be used to find the antiderivatives of quite a few different things. How about this function? I would like to find the antiderivative of 2x take away 3 squared. But I really can't do it if I leave it like that. So what I would suggest you do in a question like this is to FOIL it. Yes, foiling is still allowed. So those of you who thought I finished with factoring and foiling and I don't need to worry about it, that was my my Math 99 stuff, you are wrong. Okay, that's 4x squared, take away 6x, take away 6x plus a 9. That means we now have this guy. And this, I think, is the first time we've actually tried to find the antiderivative of an expression that has more than one piece to it. There are 3 pieces. If the world was fair and things were simple, how do you think you'd find the antiderivative of these 3 pieces?
Or over 3x cubed.
Okay, so you would find the power rule on that one.
Yeah.
This one, you add 1 to the power. You do the power rule on that one. the number 9's kind of a little bit distracting, but you actually technically the power rule also works for 9. The antiderivative of 9 is 9x, and then the plus c. I tend to think of that as a special case. So see if you have a number like 9, a constant, its antiderivative, just stick an x at the end of it and you're good to go. Now, I said that that technically is still a power rule, and I'll show you it in a minute. In this question here, do you notice that if you want to find the antiderivative of an expression that's made up of more than one piece, don't you just find the antiderivative of each piece separately? Which is nice because it's kind of obvious, but that would probably be what you should do. Let's kind of try and prove to you that the antiderivative of 9 is 9x. And I'm going to sort of prove it by showing you that you can use the power rule on it. Isn't x to the power of 0 the number 1? Right? So won't 9 be the same thing as 9 times x to the power of 0, right? 9 times 1. But I can now do the power rule, because the power rule says add 1 to the power and divide by the new power. And according to style points then, you see it's 9x. Do we feel good about the power rule as a very versatile rule for finding lots of different things that are antiderivatives? Any questions about them? None that I can see. Okay, so I'm going to give you 3 to try, and I'm giving you a minute each, so that's pushing you. See if you can get all 3. If not, at least get 1. And I'm going to give you an easy one, an average one, and a stinker. So. That's your first one. That's average. And the stinker. Okay, you got 3 minutes, no pressure, go for it. Okay, let's go for it, guys. I'll take a volunteer. What's the antiderivative of 3x squared plus 2?
X cubed plus 2x plus c.
No style points to worry about. In this second question, I hope you recognize that you have to FOIL it out. Great. What's the antiderivative of question 2 then?
You start by expanding it to x squared plus 2x plus 1, and then you just take the antiderivative of x squared, which is
Okay.
x to the third power over 3, and then plus antiderivative of 2x, which is x squared, plus the antiderivative of 1, which is just 1x or x, and then plus c for constant.
Now, the one that I called the stinker is the one that you should actually probably have been working, obviously, the most amount of time if you got to it, I hope. And I have not shown you anything like this. So this is totally out of the blue.
I know you're supposed to use replacement for it, and I got to the, I just started. I took out the constant, which is 1/2, and then I simplified it to x times x to the 4th plus 1.
Yeah, you're able to
Yeah.
like delete out the x from the bottom because you can factor out an x from the top. So it'd be x plus x cubed over 2.
I multiplied both like top and bottom by 2x. Would that work?
You multiplied the top and bottom by 2x. Anything else?
And then I multiplied 2x by on the top, and I found the antiderivative of the products of
Ah,
x.
interesting. Interesting. I'm seeing lots of different techniques. I don't have time to show you both. The two that I would have chosen, they may be very similar to yours. The first one is that when it's a fraction and there's only one thing on the bottom, you can do that. And then what I would do is I'd cancel out an x, and that would eventually become a 1/2 x, and I'd cancel out an x, and that would eventually be a 1/2 x cubed. Now, all I've done there is rewrite this in a format that allows me to use antiderivatives. Did any of you think about that technique? You may not have phrased it that way, but it was that kind of how you looked at it, right? That's totally valid. That's going to work. You can then do the antiderivative. So you add 1 to the power and divide by the new power. You add 1 to the power and you divide by the new power, and you get that. The other technique that you could have used, and I'm not saying these are the only two because I heard a few others, and to be honest, I wasn't 100% sure what some of you meant, but that's fine. If I take this as x squared plus x to the 4, and this 2x in the bottom is a problem. So I'm going to leave the 2 and then just bring up the x as a -1 power. So I heard something about x squared, but well, it might not be x squared I heard, I'm not sure now. But if you forget about that 2 for a minute, isn't x in the bottom same as an x to -1 in the top? Now, if you distribute this through, what you get is an x plus an x cubed over 2, which you can then think of as 1/2 x and 1/2 x cubed. And then the antiderivative just like before. Now, maybe it's not exactly the way that you did it, but it was in the same family as that. Did some of you think of it like multiplying the top by, well, you could have multiplied the top by that really weird looking thing. That would have probably done the same thing, but you'd have to be a little bit more careful. Did anyone come up with a totally different technique? And as long as this was your answer, or the f of x was this before you got the answer, I'd like to hear it, because you've got fresh young brains. You may have seen it a different way from me. If you got this as the correct answer, then I'm pretty sure you were doing it right. It wasn't just a luck of you did 2 mistakes and they cancelled out. I don't think that would happen in this case. Well, say hi, everybody, and bye-bye, because that's all we have time for. And we learned some cool stuff today. That doesn't look too happy. We did. We learned cool stuff today. Hey, you're a tough crowd. I think we learned some cool stuff today.
I had a question
Yes, Eric.
on I think it was in the 5.2 homework on number 5.
Oh, I'll go back to that. Okay. Give me a
Sorry.
second to no, that's not a problem. Let me get a sec to find it. 5.2, number 5. I'm just bringing it up right now. Gotcha. Okay. It's the sigma 1 e to the xi, that one.
Yeah, I'm just wondering like why we removed the i's.
Well, the xi's are being in these questions. Let me show you the thing so you can see while I'm talking, hopefully what I'm talking about. Okay. Yesterday when we did those Riemann sums, there was a point where I wrote down the expression something like this. And then we replaced the xi with all this stuff. Remember doing that? Right. So the xi's that they're talking about, oh, darn it, in space, you can't see what I'm writing. Okay, I can't do 2 screens at once, so I'll just return and show you what I was talking about here. Right. This is a typical Riemann sum for calculating the area under the curve, right? Basically, each of these represents one strip, and you're using n of them, and then you make n go to infinity, and we had f of xi, and we had a delta x. And then we did more than is necessary this time. Didn't we turn the xi into this guy?
Oh, I got really confused because on the e to the x, I thought the I was being multiplied by the.
Oh, God, I see it. Yeah, because I'm looking at it. I understand exactly because it looks like that, doesn't it? And it would have probably been much more. If it looked like that, you wouldn't have had the problem.
Mhm.
Yeah, that is just WebAssign having a very bad font, I guess. Its subscripts aren't very subscript looking.
That clears up a lot.
Right. So it wasn't the process, it was just the font.
Yeah.
Okay, that's an easy fix.